Hello everyone. In this video, we're going to talk about how to create a node in C++ so that we can get the turtle sim to move in a circle. First, I would explain how we would do it using a terminal by using normal ROS commands. And then I would go on to explain how we would write the package and then do the same thing which we did on the terminal. So first, what we do is we bring up the turtlebot sim. So ROS to um, run turtle sim node. So this will ensure we get the simulation. To understand what are the different topics being used with this node, we do ROS to topic list, and then you can see the different topics. And the one which you're interested in is the turtle1 command well, because that publishes what velocity the turtle has to move. And the next one, what we're interested in is to understand um, what what is this topic, what type of message is this topic receiving. So then we can see that the type is geometry message, message twist. And to know more about this particular message, what we can do is to do ROS to interface show, and we type the type of the message. So over here, what you'll see then is that it is composed of two different vectors, and each vector has float x, float y, float z, and the same way for the angular component. So it has a linear component, an angular component, and within that it has x, y, and z. So in order to publish some data to make this move, we need to individually assign values to each of these x, y, z. So to do that, what we can do is use this ROS to topic pub, and here you just use once, so that you just publish once and then exit, and you put the name of the topic, type of the message, and then you give it like a dictionary type of input, so linear and then x, y, z, and angular and this. So in this way, when you give this command, you can see that the turtlebot moves. So this is what we can do just by using the terminal. So now that we've seen how to do it just using terminals, we would see how we can do it using packages, which are the most efficient way to implement things like this in a more programmatic fashion. And also in the previous video, I had explained like how this ROS Qualcomm workspace is set up, and all the individual elements in that. So I would start off with how the package is set up. So we have the package and then the launch file, and inside the launch file we have the launch folder, we have the launch file, and then the source is where we have the script, which consists of the node what we're defining, and then the CMakeList and package XML. So this is an example of a node which publishes to the topic turtle sim1 command velocity, and with a message type twist. So I'm going to go ahead and explain this script, which is written in C++ to establish publishing the data on this topic. So first we define all the headers. Over here we would include the twist message which is there, which we would use, and then we would use RCL CPP because we are writing a C++ node, and this is chronos because we are using a timer which would publish the data in a specified time limit. So how we go ahead and implement this node is that first we write this class called pub node, and we inherit the RCL CPP node, and we have that in our pub node. And then we create a constructor for this class and the superclass. So here we go ahead and write the constructor node pub and then node and we give the name of this node, which is pub node, to this superclass. Next, what we do is that we create a publisher. This is how we create in C++. We write it as this, which is referencing to this instance of this object, and create publisher, which is the function, a part of this RCL class we inherited. And we do is this class, and we specify the name of the message type, the type message type being used, and then the name of the topic we are publishing to. So here we're using a twist message type, and then we are publishing to turtle1 command velocity as we wanted initially. Next, we define another timer, which we do the same way, but here we write create wall timer, and then we specify the time duration, and then we bind it with one of the method of this class, so that it keeps calling this method for every 10 milliseconds. So what we do in this class, which is binded here, is that we publish the twist message in a periodic fashion of 10 milliseconds. To do that, we create this method. This auto message, we define the message type to be geometry message twist, and then we place in the values to the respective variables inside this message, wherein we put message.linear.x is equal to 0.5, and same way for the angular z. In this way, when we publish this data, it helps the turtle to go in the circle. And here we put publisher to publish message. This is how we publish any message. And then over here we write, we initialize these variables where we define its type, which is a shared pointer. And that's the benefit of using C++, that you can use pointer and be more memory efficient. Similarly, publisher and then timer. Once this is done, you have defined this class which would help you to publish this data. Now you create the main function, and then you call upon this class, create an instance of the class, create an object, and then publish the data. So what we do is we initialize a ROS2 client library by using this command, and then this is necessary to do the following steps of creating a node. And once that's done, we use RCL CPP spin, which helps it to keep the node running. And then here we create an instance of the class and name it pub node. And this keeps running until we kill the process. And if we kill the process, RCL CPP shutdown happens, and it gracefully closes the entire ROS communication. And with this, you would be able to publish your data on this topic. So the CMake list has to be modified slightly for our purpose. Ensure whatever packages you're using, like your libraries you're using, are there in the find packages, as in RCL CPP and geometry messages. And then this is something which would not be auto-generated in your CMake list. So what you have to do is to create this executable. Because it's a C++ file, you need to show that you give the path of the CPP file, and you define the name of the executable here. And once that's done, and then you have to define that this executable depends on the following packages. This is important for your package to work. Once that's done, then you do these two things, which is install target pub node destination. This one would ensure that your your node is there referenced upon. And similarly, you do it for your launch as well. This will ensure that you can use your launch file while use your launch file by making sure that it's compiled in the CMake Qualcomm build. The launch file is pretty simple and it's more standard. When you have a node and you know the name of the executable and the name of the package, it's very straightforward. You can just use this template. You have to import launch from launch description and then import launch ROS.action from node. And then you just define generate launch and then return launch description, and you write node so that it's formatted in that particular way, and then you give package the package name, executable, the executable name which you set up on the CMake list, and then output you give it as screen, and then that's all it is for to create the launch file. So now we have written all the code needed in the package. So once we have done all that, what we do is go to the root of the directory and then build the package. So you can see that the package is successfully built. Once that's done, then you source install setup.bash. This makes sure that you source the install files. And now we can first we can get the turtle bot running. So ROS to run turtle sim node. So we have the turtle bot up and running. Now you can launch the launch file we created, ROS2 pub node package, and then we pub node.launch.py. So now you can see that it's constantly publishing, and then you can see the turtlebot just going around in a circle. So here we're not doing it through a terminal, but we're doing it through the package which we created. So once we kill this, it just stops, and we can see that it stopped moving. Hopefully you learned something new out of this video. If you liked it, please like and subscribe and follow to get weekly robotics content.